I'm Stan Krolikoski. You've heard me before. I'm here as chairman of the Design Automation Standards Committee of the IEEE, the so-called DASC, or sometimes you'll hear it pronounced DASC. In any case, part of the thing that Yatin already mentioned was that after we developed, we had 1801, UPF. It's been around for a while. We've had elements of CPF coming out of SI2 that were merged in, and this has become a good standard. However, there was a perceived need to raise the level of abstraction in looking at low power modeling to the system level. And we had the people in 1801 talking about moving upwards, and we had other people talking about moving from a high level downwards, including, as you'll hear, talking about software power and how to get, and figuring out how to get abstract power modeling done at a system level. And so we ended up, after a year of a study group, with 3 low power committees. And people were thinking, that's too many. How do they fit together? So we went through, and we had, for the first time in the DASC, a low power coordinating committee where the groups got together and figured out, okay, what is it that we're doing? Who's doing what to whom? And we met every week for a couple hours. This was primarily, this would be John Biggs, the chair of the 1801. Eric Marshner was there also. We had Nagu and Jerry Frankel from 2416, and Voin, who's going to be coming up here from 2415. And we worked and worked and worked, and eventually came up with this diagram. I had thought about talking about it here, but given the behind time, I know that Voin and Jerry Frankel, who'll be talking for Nagu in the 2416 group, have this at the beginning of their presentation, so I'll let them talk about it. But it was interesting, during the DAC workshop that Yatin just talked about, a lady named Vita from Microsoft came up, and the first thing she did was put up a slide that showed exactly this, except it was going horizontally as opposed to up and down, and it had a few different words, but it was essentially the same presentation, same idea. So either she was looking at our slides beforehand, which I doubt, or it was so obvious to her, or at least she was attending all the various meetings, that she synthesized out what we were all doing together as a committee. But that was validation. So with that, what I want to do is use the rest of our time up to lunch to have presentations from 1801 and 2415, 2416. I have to warn the 2415, 2416 people that I've applied a different template to your slides than you gave to me, even though I gave you the original template. There was some change in direction, but the colors might be a little bit different, but the message should be exactly the same. Now, Voin's looking at me like, oh my God, what did you do? Didn't change it, didn't change any word. Anyway, didn't say anything like software power doesn't matter. That would have started some discussion. But with that, let me just cut to the chase and invite Shushma up to talk about 1801. Shushma Hanavera Prasad is the secretary of the 1801. Gotta get the groups together. Right. Okay.
So good morning, everybody. We heard the emphasis for raising the level of abstraction, talking about system, and hopefully we've addressed some of those concerns in the upcoming version of our standard, which is 1801-2015. I'm not sure if it's 2015 or 16. All right, so we have the slides. I'm going to keep my presentation really brief and talk about all the new cool things that we've added into the standard in the 2015 version of our standard. So, in the spirit of going and talking about system level, we changed the title of our standard. It was Design and Verification of Low Power Integrated Circuits, and we've changed that to Low Power Energy Aware Electronic Systems. So that's the first change. We've increased our page count from 300 to 500, and we'll talk about what we've added, what information we have added to contribute to that sort of information increase. We have an internal process called Mantis, where we log changes, feature requests, what we need to do, put into the standard, what we need to change. And we had about 200 of those that we got addressed to release this version of the standard. We also wanted to simplify the standard. So in the spirit of that, we removed deleted 8 commands. We added 7 additional commands to support features like system level power, and we've deprecated 3 more commands. So the next set of slides, I'm going to talk about all the new enhanced features that we've added, which primarily surrounds, again, support for system level, information modeling, and bottom-up flow, and some other cool features that we've added into the standard. So one of the concerns we had about modeling power states was that we wanted to keep power states mutually exclusive in order to allow for correct power reporting. But as it turns out, it's not really possible to make all states, mutually exclusive. So Eric Marshner, who's the vice chair, he came up with this real beautiful explanation of all the different ways in which you can describe your power states, tie that with supply states, which is more lower level, and talk about all the conditions that lead to either mutual exclusivity or leaving a state as an abstract state, which is a requirement for some of the system level power modeling requirements. And there were other things like supporting refinement. So one of the spirit of UPF is when you start your design, you don't have enough information about your design, so you start off with something more abstract. But during the course of your implementation, like synthesis, PNR, you get more information and you want to successively add that information back into your models so that it becomes more accurate and reflects the current state of your design. And this is what we call successive refinement. And initially, we did not have successive refinement for power states, but in this version of standard, we've allowed for that as well. And I think a more general model for power states, which covers supply sets, domains, composite domains, groups, models, and instances. I won't go into the details of this. We're going to have a standard out soon, so you can get to see all that. In summary, we added commands like add parameter, add supply state, add state transition, and we deprecated the command called describe state transition. On system level power, we had a lot of discussion during the DAC system level workshops. I won't go into the details of what we did, but the spirit was we wanted to raise the abstraction of 1801. 1801 was considered to be very hardware, design, netlist, gate level centric, and we wanted to break that image and say that we can also start working at a higher level of abstraction. And in order to support that, the features that we've added is to allow for these abstracts, power states. So you have these abstract power domains for different models in your design, and you have power states for that, and you describe how you interface that with your power model. The characterization information, like how the power is computed, is not a part of UPF. How the model is activated, like the stimulus, is not a part of UPF. This comes externally. But what UPF allows you is to model the power states, the power domains, and the power state transitions. And we also clarify the definition of all the legal power states. And again, just want to emphasize that how you actually crunch those power numbers and how do you provide the functional stimulus to change from one state to another state is not within the scope of the command. We have functions to allow access to other standards that actually work to provide that information. There was one other problem with UPF, which is if you want to query what UPF is doing, we had a set of functions called query functions. And as it turns out, the support for queries was broken. And we couldn't really achieve all the things we wanted to. If you want to play around, if you want to muck around with your design and explore, do UPF exploration, that was not possible. And one thing led to another, and it led to a discussion that we need a very systematic way to represent all the information that UPF tends to provide in a very object-oriented fashion. And this was done by an information model subcommittee chaired by Amit. And the basic idea is to look at all the power management information available in the UPF, which is like UPF objects, keywords, and describe them in a very object-oriented fashion, and provide access power management functions to access that information. So we have two forms of access. You could have access functions through Tickle, you could have access through HDL. But basically, no matter how you choose to access the information, the underlying information is unified by using this information model. So on the Tickle side, we introduced like 5, Query UPF already existed, but it's kind of revamped now. We have added queries to look at object properties, object type, path name, etc. And on the HDL interface, it allows you to do abstract test benches to modify UPF objects directly in simulation. So basically, it's a very thorough and standard representation of what the power management information is and how do you access it and manipulate it either through Tickle or through HDL. So this is one of the most important additions to the standard, and that's actually one of the most exhaustive sections of the standard, almost 200 pages worth of information in the information model and the API model for it. The next part that we really worked on was to kind of help a more bottom-up friendly flow. And I'm not sure if I'm allowed to use this word, but we were trying to define what a terminal boundary is. Where is the boundary of a soft IP, and how is it necessary for us to identify it and use it to build a clean bottom-up flow? And in order to do that, we realized we have to define what a self-contained UPF is, what are the properties of a self-contained UPF, what are the implications of a self-contained UPF. So, for instance, one implication is a parent UPF cannot influence the self-contained UPF or the soft macro UPF. So we defined these two attributes called UPF soft macro and UPF hard macro. And we also added a very good flow example in the standard that describes how to use this in a meaningful flow. One other addition is probably one of my favorite additions, which was in the past in UPF, you couldn't distinguish between an HDL supply port and an HDL signal port. There was no difference between signals and supplies. And as a designer, I was finding it frustrating to see that when I am looking for a signal, it would sometimes return supply nets. So what we've done is we've actually enhanced the standard to return supply nets. And not just that, we realized that there's supply nets that are created with UPF commands like create supply net. And we've also added an enhancement to support returning UPF created objects. And it's also important to understand how this ties with the soft macro, hard macro story, because when you want to find something in your design, you probably don't want to go inside your macros. Your hard macros are probably golden, and you don't want to really go find things and change those. So it actually fits very well with the semantics because we've also defined how soft macros and hard macros are inherently leaf cells, and therefore you cannot enter a leaf cell hierarchy. So that's a new enhancement on find objects command. Level shifting and isolation is perhaps the most well-thought part of the standard because these are the two most important functions people tend to put into their designs once they start doing low-power designs. But there was a constant confusion on terminology. So when you talk about voltage, what voltage do you have in your mind? So it depends on who you talk to. If you're talking to somebody who's working on synthesis, they're talking about some corner voltage, like a min corner, max corner. And you're talking to some software guy, he's talking about the voltage he's probably going to set on the voltage regulator. So we clearly defined what these voltages are so that the tools can actually process them correctly. So we distinguish between what a nominal voltage is and what is the effect of variation on the nominal voltage, which leads you to different corners. And when you have two different voltage sources, should you consider them correlated or not? And so we have another command that talks about voltage correlation. And these are important because when it comes to identifying when you should insert a level shifter, it's critical to understand the difference between two different supplies, two different correlated supplies, and the variation on the supply versus the nominal value on the supply. And so I think that's a very important enhancement that we have in this particular standard. Furthermore, I think historically the level shifter semantics and isolation semantics, even though they're trying to do this same type of operation in spirit, were different. And one of the things we did is to align this better in terms of their behavior. Like we had an option called no shift and force shift, and we made sure that this behavior is consistent with no isolation and force isolation. So there's better alignment between what you expect with set level shifter and what you expect with set isolation. On the isolation front, we have some special types of isolation cells that don't have the need to have an always-on supply. And we call them NOR or NAND style supply isolation. And in the past, we couldn't support these type of isolation cells. We would just corrupt them in simulation. And so not only have we added support for modeling these special types of isolation cells, we've also understood the need to identify the phase of implementation. When your design is not fully complete, it's not implementation ready, the verification requirements are quite different from what you would want to verify when you actually have an implementation ready UPF. And so what we've done is we've kind of idealized the simulation behavior at an early UPF stage and enforced more checks when it comes to an implementation ready UPF stage. We've also removed some of the not so much used and probably confusing constructs like default isolation and default retention. And we simplified one more thing, which is the diff supply only option on isolation is now, it defaults to true. This is the behavior you would actually intuitively expect, but for some reason it was set to false. So we cleaned that up. So in terms of timeline, it's an interesting history. So I think it was started in 2006. There was a UPF 1.0 kickoff meeting to almost 10 years now. We are at the 1, 2, 3, 4, 4th revision of the standard. So it's been a long and interesting journey. And I'm very excited to be here because we just concluded our 10-day recirculation ballot, and we're almost about to submit this for the SASP deadline. We're very excited, so we're all set to release the standard pretty soon now. I just want to say thank you to a lot of people who are not here. First, John Biggs. As a chair of 1801, he's also the editor-in-chief. He painfully made a lot of editing changes, and this was a mammoth task, and really grateful to him for having done that. Eric Marshner, Eric was our vice chair, and he's hands-on the Mantis record holder, the person with the largest contribution to the standard. Thank you so much, Eric, for all your contributions to the standard. And the amazing P1801 working group team. I'm not sure if I got the stats right, but we are the largest entity organization, right, Stan? So, and we have lots of people and lots of energy for being a low power, standard. We have a lot of energy in our standard body. So far, I think in just 2015, we had 35 technical work group meetings, 40 technical accelerator meetings, and I think easily over 250 meeting hours of brainstorming. And I'm not sure if that number is even doing justice to some of the one-on-one conversations. David is here, so he can attest to the number of discussions and back and forth and, mulling over we did. So thank you so much for all your contributions, everybody. Thank you.